Following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are two different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmayo@ybcc.edu and I will respond as soon as I can. All right, so today we're going to take a look at the second part of section 8.2, which is dealing with functions. And so here we go. All right, so this is 8.2, part 2. When you're dividing by 0, it's undefined. If you put something into a function, if you put an input into a function and the result is undefined, then that input is not in the domain of the function. For an input to be in the domain of a function, it must produce a real output. So for instance, let's take a look at this problem. H of x equals 3x plus 6. It says, find the domain of the function. Well, there's no variable in the denominator, so there's no way that we're going to be dividing by 0. We could take any value of x, any real number, and plug it in for x. 3 times that plus 6 would also give us a real output value. So here, the domain is all real numbers. We're going to use interval notation. An interval notation, that would be the interval from negative infinity to positive infinity. Just to refresh your memory, if you've forgotten about interval notation, parentheses means that you don't include that endpoint. A bracket means that you do include that endpoint. And interval notation goes from smallest to largest. Okay? And we'll talk more about that as we go along. All right, let's take a look at another example. F of x equals 1 over x minus 4. In this case, if x is 4, we get f of 4 equals 1 over 4 minus 4, which is 1 over 0, which is undefined. So the domain is x cannot equal 4. To write that in interval notation, we want to list all real numbers except 4. So instead of going from negative infinity to positive infinity, we need to start at negative infinity, go up to but not include 4, in union with starting after 4, going to positive infinity. So this is interval notation for saying all real numbers except 4. Let's take a look at another example. Let's see here. G of x equals 5 divided by x plus 1. Here again, we have a variable in the denominator. What value of x would make the denominator 0? It might be easy to see that it's negative 1. But if it's not easy to see, you could say, well, let's just take that denominator and set it equal to 0 and solve it. Oh, when x is negative 1, the denominator is 0, the function is undefined. G of negative 1 equals 5 over negative 1 plus 1, which is 5 over 0, which is undefined. So we want to say that x is not equal to negative 1. So the domain, we go from negative infinity up to, but excluding negative 1, in union with after negative 1 up to positive infinity. All right. Let's see here. Let's take a look at this example. F of x equals x squared. Well, if we take any real number and square it, we still get a real number. 0 squared is 0. We're not dividing by 0 here. So here your domain would be all real numbers, no restrictions. And one more example. Let's see, we've got t of x equals 15 divided by 1 minus 3x. So again, if it's difficult for you to see, you could say, well, when is that equal to 0? Let's see, if we add 3x to both sides, we get 1 equals 3x. If we divide by 3, we get x equals 1/3. So we don't want x to equal 1/3. So the domain would be from negative infinity up to 1/3, not including it, in union with beyond 1/3 up to positive infinity. All right, now we're going to graph some functions, and we're going to be reviewing some properties having to do with graphing that go back to beginning algebra. They are in this textbook in chapter 3. Also, interval notation that I mentioned is in this textbook back in section, I believe it's 2.7. Let me double check here. Let's see, 2.7. Where are you? Yes. Okay. Anyway, there is a form called Slope-Intercept Form. Y equals mx plus b, where m is the slope of the line and b is the y-intercept, where the graph cuts through the y-axis. All right. So let's say we have the following function. Let's see here. I want to go back here. And we have f of x equals negative x plus 2. That's the same thing as saying y equals negative 1 times x plus 2. Because negative x, there's an implied negative 1x. So the slope is negative 1 over 1, and the y-intercept is 2. So on the graph, we've got a y-intercept at 2, a slope going from left to right, goes down 1 and over 1, down 1 and over 1, down 1 and over 1. Then after graphing several points, we can line them up with a straight edge, and maybe here we have the graph of f of x equals negative x plus 2. Let's take a look at another example. Let's say we have f of x equals 2/3 x minus 2. So again, this is in slope-intercept form. Y equals 2/3 x minus 2. The slope is 2/3, and the y-intercept is negative 2. So the graph cuts through the y-axis at negative 2 and has a slope of up 2 and over 3, up 2 and over 3. Lining up those points. And let's see here. And here is the graph of f of x equals 2/3 x minus 2. Let's see, let's take a look at another one here. F of x equals 2. Well, that's just y equals 2. If you have an equation with just one variable, and that variable is y, so we have y equals a constant, that is a horizontal line. You could also think of this as y equals 0x plus 2, which means the slope would be 0, and the y-intercept is 2. So if the slope is 0, there's no rise as you run, meaning that you would have a horizontal line. Whoops, my ruler slipped there. So this is f of x equals 2. All right. And let's see here. Let's do one more of these. To do that, I'm going to close this, open it again. go back down to this, and we have g of x equals negative 0.25x. So that's like y equals negative 0.25x. Well, the slope, 0.25 is 1/4, so that would be negative 1/4. The y-intercept, there's no constant, so that would be 0, which means this graph goes through the origin. So then we're going to go down 1 and over 4. And let's see here. And there is our graph of g of x equals negative 0.25x. Okay, yeah, my graph was off just a little bit there. I can see it's a little tricky to use this ruler on this graphing pad. Okay, now what we're going to do is we're going to look at and review, though it may be new for some of you, rules to do with graphing. And we'll talk about them in the context of some problems. This next problem says, write an equation for a linear function whose graph has the given characteristics. The slope is 5, and the y-intercept is 0, -3. Another way I could write that, recall that the letter M stands for the slope, and the letter B stands for the y-intercept, where you list only the y value. Using the form y equals mx plus b, that is slope-intercept form, we would get y equals 5x minus 3. Now, it says to write each equation for a linear function, so I'm going to replace y with f of x. So f of x equals 5x minus 3. That is a function that has a slope of 5 and a y-intercept of -3. All right, let's take a look at another example. This says, write the equation of a linear function whose graph has the following characteristics. It has a slope of 1/5, and it passes through the point 10, 1. All right. So now we don't have the y-intercept, but we do have the slope. So we could use slope-intercept form, y equals mx plus b. We could take the slope and put it in the place of m, y equals 1/5 x plus b. So we have the slope, we need the y-intercept. I can take this point and take the x value, 10, and put it there, and the y value, 1, and put it there, and I get this. 1 equals 1/5 times 10 plus b. 1 equals 10/5, which is 2, plus b. Subtract 2 from both sides, and b equals -1. Well, we know the slope, and now we know the y-intercept. So y equals mx, and then plus b. We could write plus -1, but just -1 is less work there. All I need now is to change into function notation. So there we have a function with a slope of 1/5 that passes through the point 10, 1. Okay. Now, this next one says, write an equation for a linear function that passes through. So it passes through the 2 points, 1, 7, and -2, 1. Well, we need the slope and the y-intercept. I can use the slope formula, m equals y sub 2 minus y sub 1 over x sub 2 minus x sub 1 to get the slope of the line. We'll call this first point, point 1, and the second point, point 2. So for the first point, 1 is x sub 1 and 7 is y sub 1, the subscript going with point 1. For the second point, x sub 2 would be negative 2 and y sub 2 would be 1. So now we'll go back and we'll put the numbers into the formula. Y sub 2 is 1, y sub 1 is 7, x sub 2 is negative 2, and x sub 1 is 1. 1 minus 7 is negative 6. Negative 2 minus 1 is negative 3. Negative divided by negative is positive, and 6 divided by 3 is 2. So the slope is 2. We're halfway there. We've got the slope. Now we need to find the y-intercept. Again, using y equals mx plus b, we can take the slope and put it in there. So we get y equals 2x plus b. In a previous problem, I took an ordered pair, a point that was on the graph, and plugged it in for x and y to find b. I can do the same here. I have two ordered pairs. It doesn't matter which one I choose since they're both on the line. I need to be careful. I can't pick an x from one point and a y from the other point. I have to use the same point. I'll go ahead and use point 1. So let's see here. X is going to be 1 and y is going to be 7. So 7 equals 2 times 1 plus b. 7 equals 2 plus b. Subtract 2, 5 equals b, or b equals 5. So I know the slope and the y-intercept. Using function notation, I get that. Let's go back and let's check our work. Let's take both of those points, the original points that were given, and plug them in. Let's see. 1, 7. F of 1 equals 2 times 1 plus 5 equals 7. So that one checks. Negative 2, 1. F of negative 2 equals 2 times negative 2 plus 5, which is 1. So that one checks. So both of them check. All right. Now, this says, write an equation for a linear function that passes through, passes through the point 3, 0, and it's parallel to the graph of g of x equals negative 2/3 x minus 4. Now, 3, 0 is not the y-intercept. For y-intercept, x would have to be 0. 3, 0 is the x-intercept, because when y is 0, the x value is the x-intercept. Unfortunately, slope-intercept form, y equals mx plus b, uses the y-intercept. So even though 3, 0 is an x-intercept, it doesn't give us any advantage. Well, it says that the graph of this thing is parallel to this graph. Parallel lines have the same slope. So if line 1 is parallel to line 2, then slope 1 would be equal to slope 2. Okay? Parallel lines have the same slope, and if two lines have the same slope, they are parallel. So let's take a look at this g of x. The slope is negative 2/3. So that means the slope that we want to use for our new line is also 2/3. So now I know the slope. So using y equals mx plus b, I can take the negative 2/3 and put it in the place of m. I have an ordered pair that's on that new line. So x is 3 and y is 0. So 0 equals negative 2/3 times 3 plus b. 0 equals negative 2 plus b. 0 equals negative 2 plus b. We'll add 2 to both sides, and b equals 2. So I know the slope and the y-intercept. So y equals negative 2/3 x plus 2. Using function notation, f of x equals negative 2/3 x plus 2. Let's check our work. Does this line and this line have the same slope? The coefficient of x is negative 2/3 in both cases. so they're parallel. They're parallel. They have the same slope. What about the 0.30? What's f of 3? That's negative 2/3 times 3 plus 2, which is negative 2 plus 2, which is 0. So it checks. Okay. So this is our function that is parallel to this function and passes through the 0.30. Okay. Let's see here. This one says we want an equation of a linear function that passes through 1, 2, and is perpendicular to the graph of, let's see here, the graph of g of x equals negative x over 6 plus 1. Well, first of all, let's rewrite that g of x so that it's obvious that the slope is negative 1/6. Keep in mind there's an implied 1 in front of the x, so it's negative 1x over 6 or negative 1/6 x. So the slope here is negative 1/6. Now, whereas parallel lines have the same slope, perpendicular lines, those are that meet at a right angle or a 90-degree angle, have slopes that are negative or opposite reciprocals. So if the slope of g of x is this, the slope of the line that's perpendicular, and I'm going to use that little perpendicular symbol, would be the negative reciprocal. So that would be a positive 6 or 6 over 1, either way. So the slope of the new line that's perpendicular to the old line, the slope is 6. So now I've got a point on the line and a slope. So using y equals mx plus b, m is 6, y equals 6x plus b. We have an ordered pair. X is 1, y is 2. 2 equals 6 times 1 plus b. 2 equals 6 plus b. Subtract 6. b equals negative 4. So I know the slope is 6 and the y-intercept is negative 4. So f of x equals 6x minus 4. Let's see. Are the slopes negative reciprocals? That and that, yes. If x is 1, f of 1, we get y is 2, so that ordered pair checks. Okay. Now, I mentioned a little while ago, I graphed the function f of x equals 2, which is like y equals 2, and said that a horizontal line is in the form of y equals a constant. Okay. We could also say that y equals a constant is going to produce a horizontal line, and the slope of a horizontal line is 0. We are now supposed to come up with an equation of a line that is horizontal, and it passes through the point negative 8, 12. Well, if it's a horizontal line, it has to be in the form of y equals some number. But if it passes through that point, the y value has to be 12. Writing it as a function, f of x equals 12. There we have that example. All right, now let's take a look at a story problem. This says, nurses. The demand for full-time registered nurses in the United States can be modeled by a linear function. So y equals mx plus b. In 2005, approximately 2,175,000 500 nurses were needed. Don't panic, I'm going to write all these numbers down eventually. By the year 2015, that number is expected to increase to about 2,586,500. Obviously, this problem is old. I'd be curious to know how accurate it was, but we won't deal with that right now. It says, let T be the number of years after 2000. So T equals number of years after 2000, okay? And N is the number of full-time registered nurses needed in the US. Write a linear function N of T, okay, to model the demand for the nurses. So since T is on the inside of N of T, T is our input, so that the time, the year, is the input. The number of nurses is the output, okay? So T is the input, N is the output. In a previous problem, we took two ordered pairs and used that to find the linear function. We're going to do the same thing here. We're going to go back and look at the problem and extract the information for two ordered pairs and use that to come up with a function N of T. Okay. Again, recall T is the input and it's the number of years after the year 2000. So for instance, 2005, T would be 5. 2021, T would be 21. Okay. Let's read the problem again. The demand for full-time registered nurses in the United States can be modeled by a linear function, In 2005, so T would equal 5, approximately 2,175,500 nurses were needed. So there's our first ordered pair, okay? 5 represents 5 years after 2000. 2,175,500 represents the number of full-time registered nurses needed, okay? Going on, it says, by the year 2015, so that's 15 years after 2000, that number is expected to increase to about 2,586,500. So in 2005, we needed 2,175,500 nurses. In 2015, we needed 2,586,500. Okay, again, T is the number of years after the year 2000. So we don't put 2005 and 2015 in there. We put 5 and 15 in for T. Okay, I'm going to call this point 1 and this point 2. We're going to use the slope formula. M equals y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Wait a second here. I need to leave more room there. And here. So y sub 2 would be 2,586,500. Y sub 1 is 2,175,500. X sub 2 is 15. X sub 1 is 5. All right, calculator time. We're going to take 2,586,500 minus 2,175,500, and we get 411,000. Divided by 15 minus 5 is 10. Dividing the top by 10, we get 41,100. So the slope, here, we'll say, okay, the slope is 41,100. Okay, so using y equals mx plus b, we can take the 41,100 and get y equals 41,100x plus b. Now I want to point out something. Technically my ordered pairs are t comma n. This is t and this is n. but I'm just using the X and Y form for the slope formula, etc. When I get all done, I'll change my variables to t and n of t. All right, now I need to plug in an ordered pair. Let's go ahead and use this first one. So 5 goes in for X and 2,175,500 goes in for Y. So that gives me, let's see, what does that give me? 2,175,500 equals 41,100 times 5 plus B. 2,175,500 equals, so now we're going to take 41,100 times 5, and we get 205,500 plus B. We'll subtract 205,500 from both sides. So let's see here, we're going to take 2,175,500 minus 205,500, and we get 197,000. So we get 1,970,000. Okay, let me clean this up a little bit. That's supposed to be a 5. Okay, so I know the slope and I know the y-intercept, but I've run out of room, so I'm going to take those to the next page. The slope was 41,100, and the y-intercept was 1,970,000. Let's make sure that's correct. Okay, so y equals 41,100x plus 1,970,000. But I need to use t instead of x and n of t instead of y. So n of t equals 41,100 t plus 1,970,000. And there's the answer to my first question. So there's the linear function that is a model for the demand of nurses. Okay. Follow-up question. It says, use your answer to part A to predict the number of full-time registered nurses that will be needed in 2025 if the trend continues. Okay, so 2025, T is the number of years after 2000, so T would be 25. So using function language, we want to find N of 25. So let's see what we get here. 41,100 times 25 plus 1,970,000. And I'm coming up with, let's see, 2,997,500. So that would be what? Registered nurses. Let's see here. Yeah. Okay. So what did we do? We established what the input was, T, what the output was, N, the fact that T was the number of years after the year 2000, extracted two ordered pairs, went through, found the slope, the y-intercept, created the function, rewrote it using the correct variables. All right, well, that's all I have for you today. So I'm going to go ahead and stop the recording, and I will be back at 1:15 with an office hour should you have any questions.